For this lesson, we want to evaluate the double integral over the region R of 8x plus e to the y dA. And let's define that region R. So here's the region we want to integrate over. So we need to decide what these equations are that define each of these pieces. So let's talk about that. Let's see what we have here. So here's our equations. We have y equals 4 here. I hope that's obvious. Y equals x, intercept is 0, rise 1, run 1, rise 1, run 1, rise 1, run 1. So this is y equals x. And this is rise 1, run 2, rise 1, run 2. Intercept is still 0. So this is y equals a half x. So here we go. We have these curves, but I want you to notice that if you go south to north, the southern fence is always y equals a half x, but sometimes the northern fence is y equals x, and sometimes the northern fence is 4. The fact that the northern fence changes tells me that's probably not the way I want to do this. Rather than starting south and going north, can we start west and go east? Notice the west border is always this, and the eastern border is always that. So let's think about how that's going to work. Instead of going south to north, let's go west to east. So here in essence is our region. If I start west to east, I start here and I end there. So this border in terms of x is x equals y. And this border in terms of x would be x equals 2y. So if I start with my western border, starting at y, ending at 2y. So for my region, x goes from y to 2y. And now we collapse everything onto the y-axis and ask ourselves, what's the lowest y value we see? And what's the highest y value we see? Well, I hope it's obvious that the lowest y value we see is 0 and the highest y value we see is 4. So that will be our region. And then we can go ahead and put our function in, 8x plus e to the y. Now let's talk about dA. Since x is changing first, the order of this integral has to be dx dy. So that sets up the integral for the dx dy order. If I had done it in the dy dx order, I would have had to break it up into 2 double integrals. So the other option, the less pleasant one, if I start southern border, the southern border, y would go from a half x up to y equals x. And then what does x range from? This point here is x equals 4, y equals 4. So x would range from 0 to 4. But that's just part of it because we've only done this portion. And that then would have gone 8x plus e to the y. And we would have gone dy dx plus. And then the next piece would have started where? Okay. My southern border is still here at y equals a half x. And my northern border is at y equals 4. And then what does x range from here? This is the point 48. Excuse me, 84. That's the point 84 ending there. So then what's happening here is x is ranging from 4 to 8. So that would be the way of doing that if I had gone the other direction. But you can see I have a single western border and a single eastern border. So this is preferable. That's the strategy I'm going to choose to use to evaluate this integral. So let's start with the inner integral. which x goes from y to 2y, of 8x plus e to the y dx. And remember, x is perceived as the variable here. So if I integrate 8x, that would be 8 times x squared over 2, or 4x squared. E to the y is perceived as a constant. The integral of the constant will be that constant times x. It'll be plus x times e to the y, evaluated as x ranges from y to 2y. What does that give me for my inner integral? X starts at 2y, so let's plug in 2y for x. 4 times 2y squared plus 2y e to the y. Plugging in 2y for both x's minus. Now plug in y for x. What do we get? We get 4y squared plus y e to the y. So simplifying our inner integral, what do we get? That's 2 squared is 4. 4 times 4 is 16. 16y squared here plus 2y e to the y minus 4y squared minus y e to the y. We finish up our integral with 16y squared minus 4y squared is 12y squared. 2y e to the y minus 1y e to the y is just plus y e to the y. So, of course, that's the inner integral. So our integral then will be y goes from 0 to 4 of the inner integral, 12y squared plus y e to the y dy. Let's break this up into two integrals. Integral as y goes from 0 to 4, 12y squared dy, plus integral as y goes from 0 to 4 of y e to the y dy. Working on that first piece, integral from 0 to 4 of 12y squared dy, antiderivative of y squared, y cubed over 3. The 12 over 3 is 4, so 4y cubed. Y goes from 0 to 4, so 4 times 4 to the third minus 4 times 0 to the third, and we get 256 for that first integral. Now the second integral is going to require integration by parts, so let's remind ourselves of that. Integral of u dv is uv minus the integral of v du. I'm going to let u equal y, and dv equal e to the y dy. So du is going to equal dy, or du dy is 1. Integral of dv is integral of e to the y dy, so v is e to the y. So using our rule then, integral of u dv is uv minus the integral of v du. We get the integral of u dv, integral of y, e to the y dy is uv, y e to the y, minus the integral of v du, minus the integral of e to the y dy, which gives me y e to the y minus e to the y plus c. So this is a definite integral. So I can go ahead and recognize the antiderivative is y e to the y minus e to the y. Forget the plus c, but evaluate it as y goes from 0 to 4. Using integration by parts there. And what is that going to get me? Plugging in 4, what do we get? We get 4e to the 4th minus e to the 4th minus plug in 0, 0, e to the 0 minus e to the 0. which gives me 4 e to the fourth minus e to the fourth. Obviously, that's 3 e to the fourth. Minus what? 0 minus 1. So what does that give me? That gives me 3 e to the fourth plus 1. So putting these things together then, what is my final answer for my integral? That would be 257 plus 3e to the fourth, using it with this direction. Now, remember, I also showed you how you could have done this if you chose to do the dy dx order. Now, let's go ahead and use technology to see what that result becomes. So using a double integral calculator, I have f of xy is 8x plus e to the y dy dx order. X is ranging from 0 to 4. Y is ranging from x over 2 to x. That's my first integral. And what does that give me? What do we get? We get 259 over 3 minus 2e squared plus e to the fourth. So let's write that down. And you'll notice I have that. Now we've got to go ahead and add in the other integral and see what we get. So again, same function, dy dx order. This time x is ranging from 4 to 8. That's the outer integral, and the inner one from x over 2 to 4. Let's see what we get for that. And the result is 512 over 3 plus 2e squared plus 2e to the fourth. Let's go ahead and write that down. And if we put all those together, you'll notice it looks like a lot more work than the way we did it. The 2e squareds go away. 259 thirds plus 512 thirds just so happens to be 257. E to the fourth plus 2e to the fourth is 3e to the fourth. So we did get the same answer both times, but recognize that the dx dy strategy was much simpler than the dy dx strategy.